Welcome back. Greenhouse gases, what we're talking about. We just went through all this stuff. Just a reminder, all the data that we looked at. Global warming potential is just how much a molecule can contribute to global warming over 100 years relative to a molecule of CO2. Everything is relative to carbon dioxide because carbon dioxide is like the OG when it comes to greenhouse gases. It's the one that we started studying the first. And it also looks at how well it absorbs infrared and how long it persists. So the potential when we're looking at these numbers are related to not only their persistence, not only how much they can warm the earth, but also, well, yeah, those two things. Those are the two things. There you go. All right. So potential and concentration then gives us the total effect. So because the concentration of these are lower, we don't have a huge total effect from these, right? CFCs are not huge. So if CFCs were as high as CO2, we'd all be dead. All right. So we can actually look at ice to see that it has captured gases. This is just a cool image of showing the ice that has captured these bubbles of gases. And that is really important. It's a cool image just because ice core samples is a great way for us to study the history of climate change. So let's look at some natural sources of GHGs first, because I think it's important for us to understand that greenhouse gases do occur naturally. If they didn't, the Earth wouldn't exist with people or life at all. So volcanoes are one of the main, are the first natural source that we're going to look at. Ash is reflecting the incoming radiation, which causes a cooling effect. So if we have volcanoes going off, if we have a massive volcano, it's going to block light out. It's going to cool the Earth's temperature. The next one, decomposition and digestion. Good old-fashioned just organic material doing its thing. Dead organic material converts into CO2 unless there is enough O2, right? If there's enough oxygen, then it's going to convert to, if there's not enough oxygen, then it's going to convert to methane. So this is where we're looking at, and with enough O2 is going to be oxygenated, and without is going to be non-oxygenated. The other one to think about would be, oh my gosh, respiration. We're looking at respiration. I'm trying to remember the term that I'm trying to think of. It's got oxygen or not. Anaerobic versus aerobic. There it is. Aerobic would be if there's enough oxygen, it can just convert to CO2. If there's not enough oxygen, it creates an anaerobic process, which converts to methane, CH4. So we see a lot of methane coming from landfills, and that is because there's not enough oxygen for that natural decaying to occur, which causes methane to be released. So sources of methane in nature can come from wetlands. They can come from termites. Thank you, termites. And that's it. Another process that releases some greenhouse gases into the atmosphere, denitrification. Way back when we talked about the nitrogen cycle, we talked about denitrification, which is N2O, nitrous oxide. So you get a nitrate converting into a nitrite, converting into nitric oxygen, or nitric oxide, combining with another nitrogen to create nitrous oxide, and eventually creating nitrogen gas. So N2O is nitrous oxide. That's the greenhouse gas. When it releases the N2O, that's where we get greenhouse gases. Nitrogen, not a greenhouse gas, so we don't have to worry about that. So this denitrifying bacteria, this process right here, is where we get that greenhouse gas from. Another one is evaporation and evapotranspiration. This is how we get water into our atmosphere. Natural greenhouse gas of water. You guys know the water cycle by now, I hope. This is where we're seeing that water vapor enter the atmosphere. So that is going to be the end of this video, nice and short. And then the next video, we're going to talk about increases in the greenhouse gases. How are humans making it worse?